So function A is increasing because as x gets larger and eventually will approach infinity, what happens is that the values of the function go up, and they continue to go up. So this function has a positive slope, but that positive slope changes. It becomes more and more positive. It becomes steeper and steeper as x gets larger. And that's because that first graph is most likely an exponential function. This function has a constant slope, but that slope is positive. The second graph is a linear function, so its slope always has the same value. The value of its slope never changes. It always increases at the same rate. Whereas this function always has a positive slope, but the value of the slope does vary. So here as x approaches infinity, and the value of the slope remains the same. It's what we say is constant. Now on the third equation, that function is also increasing. The function is increasing because, again, as x approaches infinity, your slope here is going up, so that's positive, going up, so that's positive, going up, that's positive, going up, that's positive. Now, the slope actually continues to go up, it continues to be positive, but if you notice what its end behavior is that even though its slope constantly changes, at the beginning it's increasing, but toward the end, or for larger and larger values of x, that slope approaches 0. Its rate of change slows down. We're not saying that it stops, because it may continually increase, but eventually it will increase so little that it'll look like it's just a flat horizontal line. Okay? So as x in this case approaches infinity, the value of the slope is going to approach some constant number. So while m is still positive, greater than 0, that slope eventually approaches 0, but we're not going to say that it actually becomes 0. Remember, we're not talking about the value of the function. Okay, we're not talking about the value of the function and what it puts out. What we're saying is that as x increases, the next value doesn't go up much higher than the last value. So we're talking about the rate of change approaching 0, not that the function itself approaches 0. the function itself is actually approaching some constant value. And the constant value that it appears to be approaching is some number k. Okay, f of x equals k. Eventually, all of its outputs will be so close to k that you won't be able to find a real difference in the rise of the function. Okay, because it will be becoming almost zero. So all of these functions that we're looking at here, every single one of them, is increasing. And the reason that it's increasing is because the slope is positive. So if those three functions represented, for example, cost in the first one, and the second one, and the third one, the cost is constantly increasing. But in the first one, it's increasing faster and faster and faster the more and more you make. In the second one, it's increasing at the same rate all the time. And in the third one, it's increasing very quickly over the first few values, but then at some point, the cost per item doesn't change very much. The cost starts leveling out, and it's going to cost you about the same thing to make 100 as it is to make 200, or 300, or 400. So your cost is flattening out if those were cost functions. Okay, and I want you to try to put all of this in context of some kind of an application, because that's the only place it's going to make any sense. These functions are all decreasing functions, which means exactly the opposite of what we said on the other one. What we're saying here is that the slope is negative. And way back when life was simpler and you were first taking algebra, you learned about this kind of a function, and you learned that this is a linear function. And the linear functions have a slope. And we know that because this slope is going downhill, this line is traveling downhill, as x gets larger and larger and larger, that means that the slope is negative. So we say it's decreasing, 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 but it decreases at a constant rate. And the value of that rate is whatever m is for that line. Remember, this is a line where the equation is y equals mx plus b. So there's your slope, your rate of change. And that's telling you that the slope is negative. The value of b is just where it crosses the y-axis. Okay? But the slope, the function in front of it, is also constantly decreasing, meaning the slope is always negative. Because as my x value approaches infinity and gets larger and larger and larger, what's happening is that my function values get smaller and smaller and smaller and smaller and smaller. Okay, so that one also is constantly decreasing. That function always has a negative slope. Now here again, notice that that end behavior of that function, it appears that it's leveling out and it's going to approach the x-axis, but it's not ever going to touch it. So eventually, even though the slope is negative, eventually the slope will be very, very, very small and be very, very close to 0. So what's happening on graph D is actually similar to what happened on graph C, except that here the function was constantly increasing. It got more and more positive as we went on, but it approached 0, and eventually the slope was going to flatten out. This slope is also going to eventually flatten out, and where it's going to flatten out is going to be when it gets closer to 0. This, by the way, is an exponential function also. The other function that we looked at here, this is an example of a function where you have y equals some number k to the x power. This is a logarithmic function. Or this is the natural logarithm of some expression. Okay? We'll call it k times x. K might be 1, k, and x might be to a power, but it's a logarithmic function. And that's what logarithmic functions look like. Exponential functions climb if they're exponential growth functions, because in this case your value of x is positive. And here your value of x is also positive. Those two functions are inverses of each other. The same thing is happening here. This is also an exponential function. But in this case, the value of x is negative, making it an exponential decay function. Okay? Remember, negative values of x would mean that that's like 1 over whatever k is. 1 over k to the x. So that means it's going to actually keep getting smaller and smaller and smaller, which is what we're seeing happen here. This is a logarithmic decay function. And again, there, x is going to be a negative number or a negative expression, a negative quantity. Okay? But notice that this one behaves just exactly like this one does as far as its rate of change. Its rate of change is negative, and it continues to be negative. But its negativeness approaches an undefined value because it's approaching a vertical line. So it's going to get very, 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 very negative. Okay, which means it's going to get very steep, but in a negative direction. It's going down. So all of those are decreasing functions. Graph in the middle decreases at a constant rate. The graph on the left, graph D, decreases at a constantly smaller rate, an increasingly smaller rate, and graph F actually decreases at a faster and faster and faster rate. Okay? Now with those basic ideas, those ideas should make sense to you because of what you do know about slope. This is the formal definition. This is the math language for everything I just said. Okay? I just tried to put it in English for you. Basically, all this says is if you move from an x value to another x value that's further up the number line, and the function value for the first x value is smaller than it is for the second one. In other words, for x1 you're here, and for x2 you're up here. That f1 is less than f2, then that tells you that the function's increasing. And it says that if x1 is up here, and f of x, or x1 is here and f of x1 is up here, and x2 is over here, and f of x2 is not as high, then that means that the value of the function is decreasing, which means it's a decreasing slope, a smaller slope, a negative slope. So let's look at this graph, and I want you to explain to me using interval language, where is this function increasing? And remember, we're talking about in terms of x values. We're going to talk about intervals. And in the intervals that we're talking about, the interval is always going to be using parentheses because we're not going to be able to include any of the points. This is always going to be the beginning. And the second value is always going to be where it ends. In other words, when does it stop doing what it's doing and change behavior? Okay? So we have several intervals here. This end of the number line is negative infinity. This end of the number line is positive infinity. So that tells us we have some beginning and ending points. So we want to decide where is the function increasing, where is it decreasing, and where is it constant. Yes, ma'am?
Well, I was going to answer.
Okay.
It was increasing.
Where is it increasing?
4,6.
Is it increasing from 4 to 6? Okay.
I think so.
I think so. There's one interval. Good. You know it's increasing because when you go from 4 to 6, what's the function doing?
It's going up.
It's going up, so it's increasing. Okay? Is it increasing anyplace else?
Yeah. Negative from negative infinity to negative 4.
Okay. Because if I go from negative infinity up to negative 4, it's also going up. Okay? So to answer my question then, where is f of x increasing? Is it increasing here?
No, it's
No,
decreasing.
it's decreasing. Is it increasing here?
It's constant.
It's constant. Not increasing here either. So the only two places it's increasing are on the intervals negative infinity to negative 4 and positive 4 to positive 6. Now notice that for those of you that remember how you write interval notation, the square bracket means the endpoint is included. Okay? And we never used a square bracket on negative infinity because negative infinity is not actually a number, so you can't include it.
But if it was a dot, you would include the brackets.
But if there's a dot, you include it with a bracket. And notice I didn't use a bracket either time here. The reason for that is because at the value, negative 4, the function is not increasing. It is not decreasing either. It changed directions. So the value negative 4 is not included in that first interval. The value positive 4 is not included in that second interval, nor is the value of 6. Because at exactly 4, it's neither increasing nor decreasing. It changed directions. At 6, it is not increasing and it's not decreasing because it changed directions. So what we actually are going to say is that here, its slope for just that one instant, that one single number, the slope of that function at that point is 0. Because anytime you go from positive to negative, you have to pass through 0. Same thing happens here. You have a slope of 0. It does not happen there. It does not happen there. And in fact, the thing that we'll eventually come to here is f of x has no derivative at that point. Do you remember why f of x wouldn't have a derivative at that point? It's not because there's a hole in the function, because f of 4 is defined. We can look at that graph and see that there is a value f of 4 right there at that little tiny corner. So f of 4 is defined, but why can't we take a derivative at 4?
Because the slope is 0 again?
No, not because the slope is 0. That's a good thought. Okay, what are the rules for being able to take a derivative? When can you take a derivative? What's the first?
It doesn't have a variable next to it. It's just constant, isn't it?
No. Go back to your rules for derivative. This is back in chapter 11. We had rules for continuity. It was discontinuous if f of c didn't exist. If there was a hole. Okay, there's not a hole. If the limit of f of x approaching c from the left and the right, if they came together, it was continuous. But then the third test was that they all had to be equal. Okay, the function meets the test for continuity because f of c or f of 4 is defined. The limit from the left of 4 is the same as the limit from the right of 4. And that's equal to the value of f of 4. But it fails even though it passes the continuity test, which is the first test for derivatives, you can't take a derivative where a function's not continuous. It doesn't pass the derivative test because there is a derivative test that says you can't take a derivative when there would be a vertical tangent, because the slope of a vertical line, which would be the tangent line, is undefined. And the other places where you can't draw a unique tangent. You remember that? How many tangent lines can I draw? I only drew a few of them. So there's no unique tangent line because this is called a cusp. Or a sharp corner in English. So it's that last derivative test that it fails. And I'm bringing that up now because I don't want you to think that as soon as it's not increasing or decreasing, that automatically means that the slope is 0, because it's not. Okay? Doesn't automatically mean the slope is 0. Now here, the derivative does exist. It exists and it equals 0. Because remember, the derivative tells you what's the slope of the function at that point. And the slope of the function at 6 is 0. So that means its derivative at the value 6 is 0. Same thing happens here. F prime of x does exist. And it equals 0. Okay? Because this is calculus, you know that eventually everything we're looking at, even though it starts out talking about algebra and slopes of lines, eventually calculus has got something to do with this. It's going to talk about derivatives. So I'm trying to bring the derivatives in to the idea slowly. Okay. F of x is increasing on the intervals that we just saw. Now where is it decreasing?
-4 to 0.
Okay. It's decreasing from -4 to 0. But again, not including either one. And where else?
6 to infinity.
Okay, that's also the correct answer. And it's decreasing because on this interval, not including that point there to this point here, but on that interval, the slope is negative. That means the function's decreasing. That also means that the values of the derivative would be negative because the values of the derivative tells you what the slope of the function is. Okay? It's also happening here. As soon as you pass 6 and go to positive infinity, what's happening is that the slope is less than 0 because it's going downhill. And that also tells you then that because the slope is found by using the derivative, that the derivative of our function on that interval from 6 to infinity will be negative. Okay? And then the last one is that it's neither increasing nor decreasing on that interval right there, from 0 to 4. And that's because its slope is 0. Okay? The value of the slope is 0. It's not positive, it's not negative. The value of the slope is equal to 0. Not the value of the function. Remember, we're talking about its slope, its rate of change. And because of that, all along that entire interval, the derivative is also going to be equal to 0 on the interval from 0 to 4. And we say that it's constant. Okay? The function is constant. It means the same thing as the slope of the function is 0. It doesn't change. It's not increasing, not going up, not decreasing, not going down. And the only thing it can be if it's not going up or going down is staying the same. That gives us a slope of 0 for the line. Okay? One of the things that it might help you to think about here, if we're talking about this function, is to think about a roller coaster. Okay? if this is a roller coaster, what's happening to your roller coaster car as it goes from 0 to right about there? What's it doing?
Increasing.
Yeah, it's getting higher and higher and higher. It's climbing the hill, okay? It's climbing the hill. It's going up. That means the slope is positive because it's going uphill, okay? But between here and about there, it's not going uphill. It's starting to go downhill. Now, it's not going downhill very fast. You know, there's not much fun when you get to the top of this little hill and go downhill. Okay, there's no big thrill there. But then from here to about here, you know, for a second, it just kind of like hits the bottom of the valley. Then it starts climbing the hill again. And you know how it works with roller coasters. When it gets to the top of a really good hill, what happens when you get here? You stop climbing the hill just for a second, just for that little brief, just about long enough to hold your breath before you start screaming. It tips over the edge and goes downhill. And it goes downhill really fast. Okay? That means if it's going downhill, the slope is negative. So downhill, slopes are negative. Uphill, slopes are positive. But when you hit a flat place, the slope's equal to 0. It's not changing. Okay? You're sitting still for a second. This is why I brought up the derivative tests. I talked about the derivatives as we were talking about that. You can decide where a function is increasing and decreasing 2 ways. You can make that decision 2 ways. The first way will fail you sometimes. In fact, with most useful functions, it'll fail you most of the time. Because you can figure out where a function is increasing and decreasing by drawing a graph of it. But if it's a complicated graph, and it doesn't fit in a standard window, sometimes it's pretty tough to figure out what to set your calculator on to actually be able to see the graph, right? I mean, sometimes we have some success if we put an ugly graph in there and we hit zoom 0, but we still have to kind of decide on a domain before zoom 0 does us any good. So while a graph will certainly let you figure out all of this, it sure as heck doesn't give you an easy way to figure it out as much as you'd like for it to. Graphic calculators are good for a lot, but it doesn't really help when it comes to trying to find out where functions that are complicated are increasing and decreasing. Especially as we've seen with the piecewise function. That gets really nasty. So what we have is in calculus, calculus gives us a derivative test so that we can tell where functions are increasing and decreasing. F of x is increasing on an interval. In other words, it's going uphill when the derivative, which is the slope, is greater than 0, or in other words, it's positive. So if you take the derivative of the function and you can figure out where the function's derivative is positive, which you can do by looking at a table of values sometimes, then you'll know that the function is actually increasing on that interval. By the same token, it will decrease on an interval when the slope is negative, which means then in turn that since slope and the derivative are the same thing, that means the values of the derivative are going to be negative. We'll tell you that the function is decreasing on that interval. Okay? And then we know when it's constant, because that's when the value of the function is just flat. It goes on with the same value for a certain length of time. In other words, when the slope is equal to 0, then that means that when we can find that the value of the derivative is equal to 0, that means we know the slope is equal to 0. It's going to be that last one that's going to be our best tool. That last one's going to be the best tool, because you can get the value of a derivative and set it equal to 0 and find out where the function is flat. Because where the value of the derivative is 0 divides it into chunks, and on one side of those zeros the function is either increasing then decreasing, or it's decreasing and then increasing. So the key to it is finding out where the value of the derivative is 0. And that's not that hard to do. Sometimes we can do it easily with algebra. Sometimes we can do it easily enough on the calculator. Okay? If you're good enough at algebra, you can solve most equations if they're set equal to 0. So that's actually what this whole first section is about, is finding something called critical numbers. The critical numbers for a function are any numbers in the domain of the function, meaning it's not points of discontinuity. It's any points in the domain of the function for which the derivative is equal to 0, or the derivative doesn't exist. Those are the two conditions. The critical point has an x value of c, and the y coordinate is the value of the function at that value, c. So if I can go back here to the very first picture we looked at for just a second. Just to illustrate this, the critical numbers for this function are -4, because the derivative is equal to 0. +4, because there is no derivative. And 6, because the derivative is equal to 0. Okay? So this function's critical numbers, actually there is one more. We didn't talk about it on that page, but there is one more critical number, and that's the number right there. And it is not differentiable at that point either, because that is, while it's not as sharp a point as there is at 4, that's considered a sharp point. I could draw many, many, many tangents at that point. So this is also a cusp, because here I could draw this tangent, or I could draw that tangent, or I could draw that tangent. It doesn't have a unique tangent. That's why it's a sharp corner. Not as sharp as this sharp corner, but it's still a corner. So its critical one of its critical numbers is also 0. And that's because the derivative doesn't exist at that point. Okay? As to why critical numbers are so important, if you can find your critical numbers, and I think a picture here is going to make more sense than these words. So I'm going to kind of push the word. You've got the words already in your notes. You don't even need to worry about writing them down, I don't think. What's going to happen here is if this is the values of your derivative, in other words, this is the slopes. Okay? Let's say I have a critical number here. And a critical number here. And a critical number here. Now those three numbers could be because either f prime of x is equal to 0, or I'm sorry, it could be, these could be the critical values of the function. So these are actually where f prime of x is equal to 0. That's why I drew them on the line. Okay, they're not above it or below it. Okay? What's going to happen at these critical values is the value of f prime of x is going to be 0. How would I know if the function is increasing or decreasing on this interval? What if I told you that from negative infinity to C1, what if I told you that the derivative's value is negative? Is the function increasing or decreasing on that value, on that interval? If the value of the derivative is negative all along that value, what's the function doing? Not the derivative. What's the function doing? Is it going uphill or downhill?
Downhill.
Going downhill. Okay, it hits the critical value. That's where the derivative is equal to 0. Then what does the function do? If it's been going downhill and it hit bottom, where's the only way to go? When you go up, what's the value of the derivative? Positive. So then what's the value of the slope? Positive, because it's going uphill. Okay? Remember, these critical values are where the slope is equal to 0. So in order to go from negative to positive, you have to pass through 0. Okay, now we've been going up, 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 up. Positive, positive, positive. Now all of a sudden the slope's 0 again. Did we hit the bottom or hit the top? Are we at the bottom of the roller coaster or are we at the top of the roller coaster? We're at the top. Because we've been climbing, right? So we hit critical value number 2. We're sitting on top of the hill. And unless we turn around and run, which means we're going backwards, what's the only choice we have?
Down.
Go down the hill. We have to go forward because x is getting bigger. Okay? So at this point, f prime of x is negative on that interval. F prime is positive on this interval. F prime is negative on this interval. And then when we hit the bottom again, it becomes positive again. Okay? Keeping in mind, one more time, that at these points, these critical points, the slope was equal to 0. That's kind of what those 4 steps tell you to do. But we're going to actually go through the 4 steps in a problem so that it'll make a little more sense to you rather than just try to read words and see what it says to do. So our example says, find the intervals in which the following function is increasing or decreasing. Locate the points where the tangent line is horizontal and then graph the function. Okay. Yes, I know you think, well, I could do that already. I can just put it in my calculator. Yes, you can. And this one, you could just put it in your calculator, but this is also one where we're going to use that ability to put it in your calculator to back up what we're going to learn without putting it in the calculator. First of all, find the points where it's horizontal, find where it's increasing and decreasing. That's talking about slope. When you're talking about slope, you're talking about finding the derivative. There better not be a person in this room that can't take the derivative of that function. What is the derivative of that function?
3x squared plus 6x minus 9.
Okay. Can you set that derivative equal to 0 and solve it? And the answer again should be yes. By some method, you should be able to do that. Either by factoring and using the zero product principle, or by using the quadratic formula, and I don't care which one you use. Find the value of the derivative. When it's 0, what is the x that causes that to happen? Yeah, you can factor it. Because the first thing you notice is I've got 3, 6, and 9. You can divide all those by 3. And the only way that's going to be true is if this is equal to 0. And there's not a lot of possibilities because there's only 2 factors of 3. That's 1 and 3.
I'll do 3 minus 1.
You want it to be positive 3 because the middle term is positive and it's positive 2. So if you take that as equal to 0, then again, this is only going to be true if either x plus 3 is equal to 0, or if x minus 1 is equal to 0. That means that x would be negative 3, and x would be positive 1. So the tangent line is horizontal . At the values x equals negative 3 and x equals 1. Okay? In other words, it's telling you the value of the slope is 0 at those 2 places. Okay? That also tells us that this function has 2 critical numbers. And the 2 critical numbers are negative 3 and 1. Okay? That's how you find the critical numbers. You take the first derivative and you set it equal to 0. Then, in order to determine where the function is increasing and decreasing, because now we know where it turns, we know where it changes from being negative to positive. We just don't know if it's going negative to positive or positive to negative. Now all we need to do is we need to test values in the 3 intervals I just created. So what we're going to do is we're going to pick some numbers. I don't want to get excited. I could pick negative 10,923.7894, but why would I do that? I'm going to pick negative 4. That would be much easier. What is f prime of negative 4? You have the calculator, you tell me.
I got 15.
Anybody else get 15? Okay, I see a couple of heads nodding. Okay. You said 15, not negative 15, right?
Right.
Okay, the fact that it was 15 really isn't the point. The fact is that it was positive. That was what we were after. It was positive. That means the function is going up. Until it gets to negative 3. Which means what should be happening in the next part of the interval is that it's going down. Should be. Okay? But we want to make sure of that, so what we're going to do is we're going to pick a number to test. And anytime I can pick 0, I love to pick 0 because 0 I don't even need a calculator for. What is f prime of 0?
Negative 8.
Negative what?
Negative 9.
Negative 9, okay.
Sorry, I didn't.
Which means f prime is less than 0, which means your values for your function are all decreasing because the slope is negative. Okay? And then it changes behavior again. It does that change at the number 1, the critical value 1. So we need to test something in this interval. And again, I could pick something huge or ridiculous. I could pick a number like pi just to make life interesting, but I don't want to. I like 2. That's a nice, easy number to do. So 3 times 2 squared plus 6 times 2 minus 9. What is f prime of 2?
15.
15. But the big point is, not that it was particularly the value of 15, the idea was that it was positive. Just like here, the idea wasn't the actual value, it was the fact that the value was negative. Okay? Now, yes, we can graph it on the calculator. Yes, we can. However, the point here is this is the way before graphing calculators were invented, and folks, you're way too young to remember this, but there was a time when there were none. When I went to college, there was no graphing calculator. We had a calculator that we were thrilled because it would raise things to a power that wasn't 2. Okay? But that was about as far as it went. It didn't do anything wonderful. I was teaching at the college level before graphing calculator became a commonly used tool. So before graphing calculators, we had to use these ideas to graph a function, period. We didn't have a calculator that would do it for us. We didn't have a software program that would do it for us. Okay?
Did you celebrate Pi Day yesterday?
I did. In fact, I celebrated it all day, and I went to Pie Night last night.
Ooh.
We ate a lot of pie.
What kind did you get?
Peach. Yeah, I like peach pie. Did you take the Pie Day quiz yet that I posted?
Yeah, I took it last night.
Okay. One of the questions, I don't remember if I put it on the test or maybe it didn't show up in your quiz or not, was what is America's favorite kind of pie?
No, that wasn't on there.
Okay. Does anybody want to take a guess of what the America's favorite kind of?
Blueberry.
Apple.
Is it pecan?
Blueberry.
If you're in the South, it ought to be calling that.
Apple.
Chocolate.
It's that's what it is here.
Is it cherry? Is it pumpkin? Is it key lime
Is it pumpkin?
Lemon meringue.
Y'all have hit everything but the one that it said, and I'm sitting there thinking,
Pumpkin.
who likes that stuff?
Apple.
Shepherd?
Shepherd.
No, that's just for mixed like me.
Oreo. Wine.
turtle pie?
You say.
Is it lemon?
Coconut cream pie.
What?
What?
Well, I think Frank's chocolate pie.
Yeah, I like chocolate pie, pumpkin pie, all those other chestnut. I love chestnut pie. But coconut cream pie. Yeah.
What does the person get like if they score the highest? What do you think they get a prize? What's the prize?
I'll tell you what it is when I get it figured out. The quiz is not done running yet.
Okay, so we get to take multiple times.
Oh, and I had people made us.
Yeah, I have. I just
Some
get
people made us up and get 100 of you got the high score.
Yeah,
You have to get it the fast.
yeah, I'm in third place 3 times through.
Okay, we burned off long enough, we only got a couple minutes, let's finish this up. Okay, we know the function is increasing until it gets to -3, then it decreases. Then it increases
Well, stop. It's not.
after it passes 1, okay?
What
What else do you know about that function before I show you the picture? What else do you know about that function? Just by remembering that the function itself, remember this is the function. What else can you tell me about that function? Just by looking at its equation. You ought to be able to tell me at least one thing.
The y-intercept is 0, 4.
The y-intercept is 0, 4. You know that for a fact.
The end behavior is down, up.
And you also know the end behavior is down, up because the leading coefficient is positive. And when you have a cubic equation whose first coefficient is positive, the highest term coefficient is positive, that means it goes up first, then it comes down, and then it goes back up, which is exactly what this says that it does. Okay? So here's the graph of the function. You knew the slope of the tangent line was 0 at -3. You knew that it had a y-intercept of 0, 4 because that was the constant at the end of the polynomial function. That always tells you the y-intercept. You knew that it had a slope of 0 because the derivative was 0 at the value 1. The only thing else you would need to do to find a good graph of that function is to actually plug in your critical values to find out where those bottom and tops are. So you would want to actually plug in your 1 and your -3 into the function. And the y-intercept, by the way, was f of 0. That was the one you really didn't have to do any work for. And then if you want to, plug in a couple more points, like those two, just to be able to figure out how fast to bring it down. So you can plug in a couple more points if you want to. You don't have to necessarily try to find that point. You can try to plug in this point. You know, so choose some easy number and plug it into and do the arithmetic, and you'll see that this is the graph of the function. But the calculus told us that this is where the function was increasing because the derivative was positive. It told us that here the function is increasing because the derivative was positive. It told us here the function was decreasing because the derivative was negative. Okay? So in order to draw the function, plug in your critical values and find f of 0. So you pick a couple more points, one that's less than the critical value, like -4, and one that's bigger than your positive critical value, like 2. You know, pick wild numbers, pick easy numbers. To get a couple more points, which are these 2 points here. And then use your derivative, results of your derivative test. Which is this part. To know where to go uphill and where to go downhill to connect up those points. Okay? Find the critical numbers and decide if f is increasing and decreasing, if f of x is this function. Now I'm going to put in some algebra steps here. You can actually work it from here, but trying to set that equal to 0 and solve it for yourself may be a little bit tough in some cases. Actually, in this case, it really wouldn't be. But you may have to do some simplification with problems like this to be able to actually set it equal to 0 and solve it. So since you know that this means that this is actually this fraction divided by that, you could actually write that as, think about this for a second, 2/3 on the cube root of x minus 1. Okay? Now the reason I showed you that is because if you were working at it from this point and you stopped here, sometimes you do need to do the algebra. if you stopped here and you said 2/3 times x minus 1 to the negative 1/3 would be equal to 0, well, okay, 2/3 is never equal to 0. And anything to a power is only going to be equal to 0 if x here, this x plus minus 1 would be equal to 0. So you're going to be tempted to say, okay, well that's going to be where x minus 1 is equal to 0. Okay? Well, that's going to happen when x is equal to 1. But if you don't carry it on out, you're not going to realize that the reason that you really can't just plug that in there is because what you're going to wind up with here is 2 over 3 times the cube root of 1 minus 1 is 0. And that's undefined. Okay? That is not defined. Now that doesn't change the fact that x equals 1 is a critical number. Okay? X equals 1 is in fact a critical number. But when you start doing your sign chart to see when the derivative is positive and negative, it's going to confuse you because if you go by what we looked at the last time, we say, okay, then at the critical number, it's going to go up, get to the critical number, go down. Or it's going to go down, get to the critical number, and go up. That won't work this time. It won't happen that way this time. So our critical number is, in fact, x equals 1. Okay, here's my critical number. So I need to test f of 0, f prime of 0. Because that's the easiest one to test. So 2/3 of negative 1 to the negative 1/3 power, or 2 over 3 times the cube root of negative 1. What's the cube root of negative 1?
That's the value of 1?
No. Cube root of negative 1. Negative 1 is the result of negative 1 times negative 1 times negative 1. So the cube root of negative 1 is negative 1. So that means that's 2 over 3 times negative 1, which is negative 2/3, which says that, okay, the derivative is negative until it gets to 1. So then we look on the other side and we say, what about 2? Okay, 2 minus 1 is 1. What's the cube root of positive 1? 1. Okay, it's 1. And 3 times 1 is 3, and 2 over 3 is 2/3. So f prime of 2 is kind of like you expected it to be, positive. But do you think that graph looks like this? Do you think that graph looks like that?
Yes, I think so. Because it's so cool. I don't know much.
Well, let's see. Is that what you were expecting? It was tempting to think,
Yeah.
because that's what you normally think, you know, decreasing then increasing, but it doesn't make a curve the way you think it does. This is in fact decreasing. It is in fact increasing. And if you go back to that function and plug in 0, you get 0 minus 1, which is -1 to the 2/3 power, and you can get an answer of -1 to the 2/3 power. You can. But it turns out to be 1. I'm sorry, it doesn't turn out to be 1. It turns out to be 0. Turns out to be 0. Okay? So here's your critical value. The critical value in this case was a sharp point. Okay? Always use your calculator to check. We'll pick up there next time. Go ahead and start working on the show me homework. Do as much as you can so I can look at it and then we'll move forward. I'll check what you get done.
When will our test be ready, Clint?
Hopefully next week. Right now they're with my student worker being marked for me to look at.
Okay. Have you looked at any of them yet?
I haven't yet, no. No, she's looking at it.
Where was the bonus problem that you talked about?
It was on the first test. You're supposed to bring it back, turn it in. Make an appointment with the testing center, have a week. Okay, so go ahead and make the appointment with them. I'm dropping off some, and I'll go ahead and fill out the form while I'm there. But just go down to the testing center and make an appointment to take the test.
Just sometime next week?
Yeah, because it'd be easier than trying to do it this week.
Okay.
So Monday, Tuesday, or Wednesday next week.
Okay.
Okay?
And what was the quiz they were also talking about?
Oh, you didn't get the reminder. Well, it's in Shelby too. There is a place, go to Shelby and go to the class discussion at the very top. And I posted the link to the quiz in the class discussion. And I sent it out on my invite.
Oh, okay.
Okay, so check those, because it's still open until midnight tonight, I think.
All right, I'll definitely have one. Thank you very much.
You're welcome.
The lesson did help. I think I understand better.
Okay,
Have a good week.
you too.
Ms. Flynn, I have a question that requires an answer from you.
Okay.
So I was supposed to take accounting 2 last semester, but somehow I passed it on. I don't know how, forgot about it, but would it be better for me to take it here or take it at ETSU?
Can you take it this summer?
No, it's not offered as a summer class. It's only offered in the fall.
Really?
Yeah, and I got my
They used to offer accounting.
they told me they used to, but they're not anymore. And I got my acceptance letter from ETSU a couple weeks ago, and then I was told whether I should take it over there or here because I'm still on Tennessee Promise.
Check over there and make sure they're using the same book.
Okay. All right.
Okay? If they're using the same book, then my answer is, yeah, just take it over there.
Okay.
And
all
then
right.
transfer it back over here, and you'll actually have your associate's annual still
Yeah,
be transferred.
because they said I can still walk the stage. I won't
Yeah.
be receiving anything, which kind
Yeah.
of bumps me out.
Yeah, but you will. You'll just get it at the end of at the end of the fall semester
Yeah.
when you finish it.
Okay.
But check with them about the book first,
Mhm.
because if they're using a different
Yeah.
book, and you have to buy another book
Mhm.
in addition to paying for the course over there,
Yeah.
you're better off paying the tuition to take it over here
Then over there.
than over there, and then take the rest of your course load over there. Just come back here for that one accounting class.
All right. Okay. So should I still
Did
like?
you do really good? Do okay in accounting one?
I'm in accounting 1 right now. I'm sitting at an 8 right now.
Okay.
Yeah.
So if you had to, you probably could do it as an online class.
Mhm.
Yeah. Well, you could probably do our online class. in the
Yeah.
fall.
Okay. I'll probably do that then.
Okay.
All right. Thank you, Ms.
Yeah,
Flynn.
that would be my advice, just
Okay.
from a money standpoint.
All right. I'll ask around just to make sure, just to double make sure on everything.
Yeah, and you can call over there and find out what their accounting to, what their publisher is,
Yeah.
their accounting to book.
All right. All right. Thank you, Ms. Flint.
You're welcome.